Okay, this is section 2.7, and we're going to talk about all the different types of parent graphs that we can have. So the first one that we're going to talk about is y equals x. This is a linear equation that you will see all the time, and you need to be able to recognize what the graph of that looks like. So we're going to do it two ways. We are going to fill in our t-chart, and then we could also graph this if we wanted to by using our slope intercept and do it that way. So when I plug -5, when I plug these x values in, okay, I'm going to plug it into the x, and then I would see what my y value would give me. So do you see that this, when I plug x in, I'm going to get that same number back. So when we're filling in our t-chart, that's what my numbers are going to look like. And then this t-chart is just giving me ordered pairs. Okay, when x is -5, my y is -5. When x is -4. So I have, if I plot all these points, then you wouldn't have to necessarily plot all of them. Okay, you see, I have this line. I'm going to try to connect these. Sometimes it's hard to get it. Okay, so here's my line. And that's the line of y equals x, which makes sense. My y-intercept is 0, my slope is +1, so I go up 1 over 1. Okay, now we're going to write the domain and range for each of these. Okay, my domain are my x values, and if I continue this graph on, then my domain are all real numbers. Okay, or I could say I'm going to go from -infinity to +infinity. Okay, that's one way to write it, or another way to write it would be all reals. Okay. Now we're going to find our range. Remember, our range are my y values. Again, this would keep on going up all the way and down all the way. So my range would be the same thing, -infinity to infinity. Or I could write all reals. Okay, and then special features of this function. Sometimes this function is known as the identity function. So anytime I say the identity function, this is what I'm talking about, the line y equals x. All right. Now it doesn't ask you to graph it, but if I wanted to graph the line y equals -x, it's the same line, but it's going the opposite direction with a negative slope. Okay, so -x would look like that. Okay, so y equals x is an equation, a linear equation that you need to be familiar with. Second one, y equals the absolute value of x. So first of all, you need to fill in your x numbers, and we're going to use the same x numbers on all of these. We're going to go from -5 to +5. And then when I plug these x values in, when I plug -5 in, y equals the absolute value of -5. Well, we should know the absolute value is always positive, so this is a +5, +4, +3, 2, 1, 0. 1, 2, 3, 4, 5. And remember, I'm getting all these numbers by plugging it into this equation. So when I graph these ordered pairs, I get these points. Okay, so -5, 5. So to the left 5, up 5. The point -4, 4. To the left 4, up 4. And I graphed all of those. So when I connect these, here's the graph of y equals the absolute value of x. It's a v. Okay, so we should all remember that. Always remember the absolute value of x is always that v. And remember, this is a sharp corner right here. You can't round it off. All right, so my domain, remember, are my x values. So how far left and how far right does this graph go? Well, it goes from -infinity to +infinity. So -infinity to infinity. My range is how far up and how far down this goes. They're asking about the y values. Well, this goes, the lowest point is 0, but then it goes up. So my range is 0, and I can put a bracket because it includes 0, and then it's going to go up to infinity. class notes or special features. Okay, what you need to know about this is this can be written as a piecewise function. The equation of this line right here is negative x from our previous problem, but it's only negative x where x is less than or equal to 0. And then this line right here is positive x where x is greater than or equal to 0. So special features of this function, it's a v, and it can be written as a piecewise function. All right, example 3, the parent function of y equals x squared. So again, we're going to fill in our numbers. Okay, this time when I plug these in, y equals negative 5 squared. That gives me a positive 25. I'm plugging it into this x right here. When I plug in negative 4, negative 4 quantity squared is positive 16. Negative 3 quantity squared is 9. Negative 2 quantity squared is 4. Negative 1 quantity squared is 1. 0. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. Okay, so we can plot these points, but I'm going to run off my graph, so I'm just going to plot the points that I have. Okay, well I have the point 0, 0. I have the point negative 1, 1. And I have the point 1, 1. I also have the point negative 2, 4. So negative 2, 1, 2, 3, 4. I have the point 2, 4. And then I have the point 3, 9. And I also have the point negative 3, 9. Okay, now for x squared, when I connect these points, this is a nice rounded bottom, and it's not a V like our absolute value. Okay, so that's what the parent graph of y equals x squared looks like. Our domain, how far left and how far right does this go? Well, it's going to go from negative infinity to infinity. Even though it looks like it stops here, it doesn't. It could keep on going. Our range, or our y values, how far down, how far up does it go? It starts at 0 and goes up to infinity. Special features of this function. Okay, this is called a quadratic function. It's also called the squaring function. And it will always make a parabola. Okay, so it's quadratic. Anything that's to the second power is quadratic. It's also known as the squaring function. And then it will always make a parabola whenever we graph it. All right, example 4. Y equals the square root of x. Okay, so on this one, if I use my regular numbers that I've been using, okay, I cannot plug in a negative number because I cannot take the square root of a negative number. Okay, because anytime we square something, it's always positive. So this is impossible. So I'm not going to have any of these numbers. Now I can have 0. The square root of 0 is 0. The square root of 1 is 1. The square root of 2, well, I don't know what that is. So if I put it in my calculator, the square root of 2, it gives me this decimal, 1.414. Square root of 3, that's not a perfect square, so it's going to be some weird decimal, 1.732. Square root of 4, we know that, it's 2. Square root of 5, we don't know. Okay, so square root of 5 is 2.2 something. Another one that I might add to this is 9, because I know the square root of 9 is 3. Okay, so these points right here, I'm not going to have any points there, okay, because I don't have a y value. So I'm going to start at 0, 0, There's this point. I can have the point 1, 1. I have the point 2 and 1.4. So 2, 1.4, somewhere around there. 3, 1.7. 4 is 2. 5 is 2.2. And I know that 9 is 3. So when I connect these, it looks like that. That's what the graph of y equals the square root of x looks like. So the domain, our domain is our x values. How far to the left and right does it go? Well, this time it doesn't start. It doesn't go all the way to the left. It starts at 0. So my domain starts at 0 and it goes to infinity. My range, how far up and down does it go? Well, again, it starts at 0 and it's going to go to infinity. Okay, class notes, this is called the square root function. And then just kind of an interesting fact, if I put the square root of any number in my calculator, I don't know, like 13, and I keep taking the square root of each answer that I get, eventually I will always get to the answer 1. No matter what number I started with, if I keep taking the square root of my answer, I'll eventually get to 1. So that's kind of just an interesting fact. All right, number 5. The parent graph of y equals x cubed. My little cubed kind of went away. So -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5. And this time when I plug each one in, -5 to the third power. Okay, so -5 to the third power is -125. -4 to the third power, -64. -3 to the third power is -27. -2 to the third power is -8. -1 to the third power is -1. 0 to the third power is just 0. And then 1 to the third is 1, 2 to the third is 8, 3 to the third is 27, 4 to the third is 64, 5 to the third is 125. So obviously we can't graph all these points, but we can graph the ones here with arrows next to them. All right, so -2, -8, -1, 1, 0, 0, 1, 1, 2, 8, and 327 way up there. So here's what the parent graph of y equals x cubed looks like. It's going to go like this. Okay, and often I'll refer to this as an S-shaped curve. Okay, so my domain for this, for x cubed, even though it looks like it flattens out here and it only goes to, let's say, -4, it's going to keep getting wider and wider as I go. So my domain is -infinity to infinity. My range is -infinity to infinity. Okay, special notes of this. This is called the cubic function. And in calculus, you will learn that at the point 0, 0, I have a point of inflection. The point of inflection is just where a curve changes its concavity, so, or its curvature. So it changes right there. Okay, number 6, y equals the cubed root of x. All right, so let's see here. -5, -4, -3, -2. All right, so when I plug in the cubed root into the cubed root of x, whoops, 1 divided by 3. Okay, so when I plug in -5, so here's what I'm doing, the cubed root of -5, and I just stuck this in my calculator. They give me -1.71. The cubed root of -4, that's going to be -1.587. When I type in -3, -1.442. -2 is -1.26. -1 is -1. 0 is 0. 1 is 1, and then 2, these will share the same numbers, but they're going to be positive. One number that I probably should have included on here is 8 and -8. Okay, when I plug in 8 and -8, this is going to be -2 and +2. All right, so we're going to plot the points that we can. Okay, and we can plot all of them. It's just kind of hard to see where they might be. So the ones with blue arrows might be good ones to plot. So I have -8, -2, -1, -1, 0, 1, 1, and 2, 8. I'm sorry, 8, 2. So here's what this one looks like. I knew that didn't look right. Hang on, I graphed this wrong. 8, 2. Sorry, 8, 2. Okay, so doesn't this look familiar? This looks a lot like my S-curve, which is this one right here, but it's flipped over on its side. And that makes sense. This is x cubed. This one is the cubed root of x. Okay, so my domain, -infinity to infinity. My range, -infinity to infinity. Okay, class notes, this is the cubed root function. And that's about it on that one. All right, number 7. Parent function y equals 1 over x. So -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5. All right, so when I plug these into this equation, I get 1 over -5, 1 over -4, 1 over -3, 1 over -2, -1. This one, I can't put 0 on the bottom. That's undefined. Then I'm going to have 1, 1/2, 1/3, 1/4, 1/5. Okay. So when I graph this, okay, I can plot point -1, -1, 0. I'm not going to have a point. I can plot 1, 1. Here's what this one looks like. Okay, we haven't really talked about vertical and horizontal asymptotes yet. But the graph of this doesn't look very pretty, but you get the idea. Is that right there? Okay, and this is a nice curved shape. It shouldn't look so much like an L. In fact, I should probably fix that. It's a nice, neat curved shape. Let me get my pen back. Crosses through 0.11. It's just kind of hard to do it with this keypad. Okay, so my domain are what x values can it include? Well, I can include any x value that I want except for this one right here. I can't include 0. So one way we could write it would be -infinity to 0 unioned with 0 to infinity. Or I could put all reals except x equals 0. My range is the same way. Okay, my range is going to include all the numbers except 0. Or all reals, all reals, except y equals 0. Or we could do it like this again. Class notes, this is called the reciprocal function. And later on, when we're graphing conic sections, you'll learn that this is the graph of a hyperbola. And hyperbolas are often used, the reflection property is often used in satellite dishes. Okay, so that's a hyperbola. All right, number 8. Okay, the parent function is y equals 1 over x squared. So if I choose my numbers, all right, I plug these numbers into 1 over x squared. So -5 is going to be 1 over 25. This is going to be 1 over 16, 1 over 9, 1 over 4, 1. This is going to be undefined because I can't have 0 in the denominator. 1, 1/4, 1/9, 1/16, 1 over 25. So again, we're going to have some really small numbers. So let's do the ones that we can. We can do this one, and then you can tell that they're getting closer and closer to 0 the further I get. All right, so I know it's going to be -1, 1, and 1, 1. It's going to pass through those points. And this one's going to look very similar to the one we just did, except both of them are going to be up here. So my domain on this is going to be -infinity to 0 unioned with 0 to infinity, or all reals except x equals 0. My range in this case, okay, my range, the lowest value, it's going to get closer and closer to 0. So I could say 0 to infinity, or I could write y such that y is greater than 0. And I don't have any class notes written down for this one. And the last one, I believe, y equals 2 to the x. Okay, so let's do our numbers. Okay, this time I'm plugging these values. This is going to be like 2 to the -5th. All right, so when we plug that into our calculator, when I plug in -5, I'm going to get 1 over 32. All right, when I plug -4 in, I'm going to get 1 over 2 to the 4th, 16. 1 over 8. 1 over 4. Okay, so -4, -3. Oh, whoops. 2. I'm fixing something real quick. Sorry. Okay. So this is going to be 1/2, 1, 2, 4, 8, 2 to the 4th is 16th, 2 to the 5th is 32. Okay, so let's just plot some of these points. Okay, I can plot this one and then the rest of them. So negative 1, 1/2. 0, 1, 1, 2, 2, 4, 3, 8, and then 4, 16 is going to be way up there. And then as I get closer and closer here, it's going to get closer and closer to 0. So it's going to look, oh, I don't know what happened. Oh, all right, so when I graph this, it's going to get closer and closer to 0. So it's going to look like this. Okay, so my domain are my x values. Okay, my domain are all reals or negative infinity to infinity. My range, the lowest that this is going to go is going to be 0 and the highest infinity. Class notes, I don't have any class notes for this one. Okay, so what you're going to do is you're eventually going to have to memorize what each of these graphs parent functions look like, because we're eventually going to start doing things to these parent graphs. We're going to translate them, shift them over, shrink them, things like that. All right, so I will see you on Monday.